homework problems. Zhao, trying to remember these names. Ao. No. Zhu, Zhu, Shu. Shu, right? Shu. Okay, Seth. Got that one. Wang. Wang?
Wang.
Wang. Okay, Zhai. Okay, so I'm missing Zhao. She's right there, except she isn't. Okay, let's wait a couple minutes. They'll probably come in. If not, then... Anybody have any questions before we start?
About the simulation, I haven't considered.
Have you done that? Have you tried it, or?
So this first part is it seems that the
Theory?
theory, right?
Yeah.
The theory is pretty simple.
Yeah. But wait, okay, if we're going to discuss it, let's get on tape and then, because maybe I don't know if they're going to be here or not. Oh, here they come. Okay. Now we can start. Okay, we're ready to go. Are we on? We're on. Okay, are there any questions? You were asking about the simulation, right?
ER, the value of ER for the theoretical part is just the formula. We
Yes.
directly use the formula, right?
Yeah, it says draw the graph of ER versus U. So what you do is you calculate the expected value of R using the formula that we derived from renewal theory.
Tau here is the expected value. EX is tau.
Yeah, that's what we called it, right?
Sigma square is the variance.
Right. This is straightforward. I mean, it's simple.
Straightforward, a little bit like this.
Yeah, but there's something surprising about it, right? Is that why you're asking the question?
Not really, since you changed the
What you're asked to do is to calculate for this renewal process. Okay, we have a renewal process, and the times between renewals we're calling x. And here's some point t. And that breaks one of these renewal intervals in two pieces. And then there's this time r. In equilibrium, of course, this t is an infinite distance away from the origin. And we want to calculate the expected value of r. And you want to plot it as a function of u. Now, the x, that is the interrenewal time, x is equal to u plus y, where u, for our purposes, is a constant. We'll treat it as a parameter, and y is a random variable whose distribution you're given. So when you calculate this expected value E of r, it contains the expected value of x, and it contains the variance of x. So for any given value of u, you get some formula, some value. Okay, now, if you vary u from 0 on up, then what happens is that the expected value of x is a linear function of u. But the variance of x doesn't change, because if u is a constant for any given u, then the the variance of a sum is the sum of the variances, and the variance of a constant is 0. So the problem is constructed so that different values of u correspond to different values of the average time between arrivals, the different values of the average interrenewal time. So what's happening is, as u gets bigger, that means that the process we're looking at is a process whose average x is bigger and bigger, but whose variance remains the same.
Yes.
Okay, so the intuition would tell you that as u gets bigger, since u represents the fixed portion of the interrenewal time, as u gets bigger, then the average value of r should also get bigger, because what happens is the r interrupts one of these x's, and so if the x's get bigger, then the r should get bigger as well. In other words, you would intuitively expect that as the average time between renewals gets bigger, that the average waiting time from a random point until the next renewal should also get bigger. Now that could conceivably be changed by making the variance bizarre. You could change the variance at the same time, because you know the variance is going to have an effect here. So what this problem does is it changes the expected value of x without changing the variance. So the amount of variation in these intervals remains the same, but the average length of the intervals gets bigger. Now the surprising thing is, I guess you should all know by now, is that if you plot this, you will find that the answer looks like this. In other words, there's a minimum. It first decreases as u gets bigger, and then it increases as you would expect. So this is pretty surprising. In fact, when I first realized this, I didn't even believe it. I'm still not sure I believe it, so that's why I'm asking you to simulate it to see if it's true. So I haven't written a simulation, although the theory says it must be true. So if the theory says it must be, then it is. So what I'm asking you to do is simulate it and plot the points, the simulation points, and run each simulation point long enough so that you're pretty sure that it's accurate. Because there isn't much difference between here and here. And so that effect could get lost in noise. But if you know it's there because the theory predicts it, then the simulation, you could run the simulation long enough until you're sure that in fact the simulation and the theory agree. If they don't, of course, something is wrong, and maybe you would expect something is wrong, because this seems to me to be a completely counterintuitive answer. But what I'm asking is for you to get these points like this, specific simulation points, and hopefully what they will show is that the prediction of the theory, which is that at first the average forward recurrence time decreases, reaches a minimum, and then increases, is in fact correct. Then the next question, which I didn't ask, but which is obvious, is, well, how do you explain this? How can this possibly be? So if it turns out that the theory predicts it and the simulation verifies it, then it must be true. And then the next question is, well, how can that be? Because, at least from my intuition, it's completely counter to everything I would understand, think about these kind of processes. Now, the value of t here, this value of t has to be far enough away from here to be in equilibrium. So what I said was take t to be 100 plus 10 times z. Where z is an exponential random variable with average 1. So that means that the average distance of t from the origin would be 110 units, but it would vary. It would be at least 100, but very unlikely to be much more than the 120 or so. So you're going to have a window here in which this t is going to vary. I don't know how important that is, and I don't know whether this 100 is appropriate, because if I make this number too big, then it takes a long time to get there, which means the simulation runs a long time, which is just inefficient if it's not necessary. And if I make this number too small, then the t is going to be too close to the origin. The important thing is that this is chosen only to make this value of t far enough away and to make it so that it doesn't seem to be synchronized in any way with the x's. So if you can get the results you want by making t smaller or generating a different way, that's okay. I mean, I just made this up. Okay? Okay, but basically what you're doing here is you fix a value of u, and then you reach into the urn and pull out these x's, and you fix a value of t, and you lay off those x's until you have an r, and then you record that r. And then you fix another value of t, and then you go back here and you sample from this urn again. And you do that 100,000 times, so that means you have to generate 100,000 of these t's, and you will then get 100,000 of these r's for each individual u. So this may take time, and that I really don't know. And remember that I just want to get the result. I'm not really interested in how long it takes. So if less than 100,000 is sufficient, that's okay. You have to play around with this. If it takes 1 million, or if you can get 1 million, well, that's fine. Based on how fast the program runs, the bigger the numbers are, the more accurate the results are. Okay, so you have to do that. So you have to make 100,000 different replications for each of these points, and there's about 5 different points that are given there.
Actually, you have to create more than that. This is every time you have 90%. Take y take 1, and 10% y take 11. You have to consider the possibility.
Oh wait, you have each replication is a value of r, but in order to get r, you have to generate a whole bunch of y's.
Yes.
And maybe you have to generate 50 of those. I don't know how many you have to generate.
It depends.
It depends, yeah.
The random selection.
Right, it depends. So it may be that what I'm asking you to do, to run the simulation actually takes too long. And if it does, then all I can say is, okay, after you've experimented with it and it looks like that's what happens, then make t shorter, or don't do it 100,000. What I'm asking you to do is, I don't want to tell you everything, especially since I don't know everything because I haven't done it. What I'm saying is, I have this theory, and the theory, if I understand things right, predicts that as u gets bigger, the average value of the remainder of the interrupted interval gets smaller, although not a lot, but nevertheless it does in fact have a minimum, and then it starts to increase. And that is a very surprising result. So I want to see whether it's true. So to see whether it's true, I'm asking you to simulate this. And so you want the simulation to be as accurate as possible. And I want the simulation points to be at those places that are important, like where the minimum is, and just before the minimum, and just after the minimum. Okay, so the experiment, I mean, look at this as this is an experiment in which I'm asking you to design a simulation experiment that will confirm this counterintuitive theory, or not confirm it if in fact it's wrong, although I don't think it's wrong. So do we have any preliminary results so far, or anybody have any feeling as to what's happening? Haven't done it. What was that?
I want to figure out how can we do it. Since according to this, it's just found the one, the later arrival minus t, it's the r, right?
Yes.
You do 100,000 times.
Yes.
And take an average.
Yes.
And compare with this.
Yes.
Theory.
Yes. Right. But maybe 10,000 times is enough.
I tried it first, 1,000.
Right, right. The trouble is that what you're trying to do with the simulation is you're trying to check to see whether or not there really is this strange effect that as u gets bigger, the average value of r gets smaller. As I say, that to me is unbelievable at first. So, and the difference between here and here is not great quantitatively, but qualitatively, the theory definitely predicts a decrease and a minimum and then an increase. And so you want the simulation to be accurate enough so that it actually gets that result. If the sample size is too small, well, you're going to get points that are going to look like this, and then you're not going to be able to tell whether the minimum is real or whether it's noise. So you want to make the run long enough so that you're convinced that whatever you decide from the simulation is in fact correct.
When you decide t take that form, which means t is also a random.
Well, the reason that t is random, it doesn't have to be. I could take t to be 100 every time. I'm just trying to
Yes.
guarantee that there doesn't turn out to be a synchronization between the process and the value of t. Because if there is, then this is really not a random point. And then that means that there'll be some kind of bias which could work in any direction, who knows. The theory is under the assumption that this origin is an infinite time away. But I can't, of course, produce an infinite number of these, an infinite length of time. So I'm trying to compensate for that by making it far enough away, and at the same time putting in another element of randomness so that there is less likelihood that there's a synchronization or connection between the value of t and the origin. It may be that if you simply use t equals 20, period, that would work. But I don't know that, I just wanted to be sure. But you can experiment with it. All I want you to do is to convince yourself that the theory really does predict the minimum and that the theory is right. There really is a minimum. Or it's not right. If it's not right, what's wrong? And if it is right, how do you explain this? Because this is certainly, I think, completely the opposite of what anybody's intuition would tell them. Certainly the opposite of what my intuition would tell me until after I knew it was true. Because I haven't seen the simulation, I've only seen the theory. But the theory tells me it's true, but since I believe the theory, I don't need simulation. So then after I decided it was true, then I convinced myself that of course it has to be true. But that may just be casuistry, as they say. I mean, sometimes in probability you can convince yourself of anything if you try hard enough. Okay, so this is a real experiment. Should be interesting. Okay, any questions about that? All right, so now we're actually ready to start working on Qs. This all is background stuff for Qs. Now what we've done so far is we derived by a probabilistic argument using pasta and the fact that the arriving customer's distribution, the outside observer's distribution, and the departing customer's distribution are the same in Little's theorem. Using all of those arguments, we were able to come up with an intuitive argument as to why in MG1, Poisson input, general service times, one server, that the expected value of the waiting time had a certain formula, namely rho times tau divided by 2 times 1 minus rho times 1 plus sigma squared over tau squared, where in this formula, rho is the utilization of the server. That's the arrival rate times the average service time. Tau is the average service time. And sigma squared is the variance of the service times. And this can be rewritten as rho over 1 minus rho times tau over 2. I'm just multiplying through here now, plus sigma squared over 2 tau. And when you look at it this way, you recognize that this is in fact the expected value of the forward recurrence time of a service time. And that was the way we derived it. We derived it by making the argument that when a customer arrives, there are two possibilities. Either he finds the server idle, in which case he makes it busy and his waiting time is 0, and that means that you have then a sequence of these service times called the busy period. Or when the customer arrives, he arrives in the middle of someone's service time. If he has to wait, he must have arrived in the middle of someone's service time. And in that case, then his waiting time will consist of the remaining service time that he interrupts, plus the sum of the full service times of all of the customers ahead of him. But surprisingly, all of that works out to have just a piece here which represents the remainder of the interrupted service time if in fact the process were a renewal process. That is, if you had, if in a renewal process, these x's corresponded to the service time. But this really is not a renewal process because we have these gaps caused by the times when the server goes idle. But I argued that, well, that really shouldn't matter because those are exponentially distributed times, so why don't we just forget about them and imagine that we just merge these two processes, these busy periods, and then we wouldn't have to worry about that. Well, that's intuitive. It can be justified. But now what I want to do is I want to treat the whole problem. And I want to calculate not just the expected value of W, I want to calculate the complete distribution of W, and then show that this famous formula, the Pollaczek-Kinchin formula, drops out. And in the analysis I'm going to do, I'm not going to make use of any of these, I'm not going to make any assumptions. We're just going to go right from the beginning, or at least no assumptions that we've made before. So now everything is going to be from first principles. Okay? Okay, so now for the first time we're actually getting into real worrying only about the Q's and not about all of the stuff that underlies it. So I'll start with equation 813 on page 212. What I'm going to do is I'm going to define NK star. So this is my definition here. N sub K star is equal to the number of customers left behind by the kth departure. Now, the reason I'm looking at left behind is, let's look at a queuing process. The customer arrives. Let's say he finds the server idle, so he makes it busy. The next customer arrives. Now, the next customer arrives, either he finds the server idle again, or he finds it busy. If he finds it busy, then he necessarily interrupts somebody else's service time. But if he interrupts somebody else's service time, then if I try and look at the system from the viewpoint of the arriving customer and the state that he sees, then I have to take into account the amount of time that remains, or the amount of time that has been used up on the service time that's interrupted. And unless we have exponential service times, that introduces memory. And that's the problem. So if I don't have exponential service times, then I have to recognize that it's very difficult if I analyze the system from the viewpoint of the arrival, because the arrival is going to arrive in general in the middle of a non-exponential service time. So I'm going to have some way of keeping track of how much service time has been used up and how much service time remains. So to get around that problem, what I'll do instead is I'll take the viewpoint of the departing customers. Now, when a customer departs, there are only two possibilities. Either he leaves the system empty, or he doesn't. If he doesn't leave the system empty, like right here, for example, then what you know is that a new service time will begin, and that service time will begin at the beginning. And so therefore, there won't be any memory problems to worry about, because the points at which I'm going to look at the system are points in which every service time, either there is no service time, and the system is empty, and I just wait until the next arrival occurs, or if the service time has just ended and somebody else is waiting, then that new service time starts in the beginning. And I know the distribution of service times as a whole. What I don't know, or what's difficult, is the distribution of a partial service time. So what I'm going to do is I'm going to try and get around the problem of memory by considering the system only at the service completion epochs. So that's what the star corresponds to. Because remember, earlier we talked about pi star, which was the probability from the viewpoint of the departing customer. So this random variable is the number of customers just after the departure of the kth customer. And now from that, I can easily write down a formula using the theorem of total probability. I could say, what's the probability that the kth plus first departing customer leaves the system in state J? And I'll just use the theorem of total probability to condition on the number left behind by the previous customer. So I'll say the probability that the kth plus first leaves behind J is equal to the probability that the previous customer, the kth, left behind I times the probability that the kth plus first left behind J, given that the preceding customer left behind I, summed over all I. So that's the theorem of total probability. It's true. Of course, we don't know if it's useful or not, but it's certainly true. Okay, the probability that a customer leaves behind J is the probability that the previous customer left behind I times the probability that the customer, the test customer, leaves behind J, given that the previous customer left behind I. And what we want to do is we want to be able to find the, ultimately, the equilibrium probability that a departing customer leaves the system in state J. Okay, so that's equation number 813 in the text. Now, one of the questions is, even if it's true and even if it's useful, that is, even if we can solve it, so what? Because what we then have is the state distribution from the viewpoint of departures, and of course what we're interested in is the state distribution from the viewpoint of the arrivals of the outside observer. Of course, I could, if I were to be able to solve for this, I could then invoke the theorem that says that the departing customers see the same state distribution as the arriving customers. We've already made that argument in equilibrium. And that if the arrivals occur according to a Poisson process, then that's also what the outside observer sees. But it's really not clear at first glance that, except for applying those theorems, that there's really sufficient information here to get what I want. This was a confusing point when this stuff was done originally. And by the way, this analysis, which is called the embedded Markov chain. Okay, I'll write down that. Those are important words. Embedded, sometimes spelled with an I, sometimes spelled with an E. Markov chain. Okay, this idea was introduced by Kendall in several papers written in the 1950s. And essentially what Kendall did is he took queuing theory and he made it accessible to a much broader population than was able to understand the mathematics before this. When Polacek and Kinchin derived this stuff, the level of mathematics was much higher than what Kendall did. Kendall introduced a method that greatly simplified things, applies to lots of other cases, and without it, we'd be nowhere in queuing theory. Now, embedded means that there's a continuum of points here. This is time. And embedded means that the points are stuck in. That's what the word embedded means. They're stuck in this continuum. Now, a Markov chain is something from elementary probability, which describes a process with discrete states. And it's assumed that there are discrete trials, and at each trial, the state jumps from one state to another state, and the only thing that determines what state I jump to is the state that I'm in, and not the prior history before that or how long I've been there. Well, it'll turn out that this, in fact, is a Markov chain. But the discrete trials are, in fact, the instance of departure. So the chain, in a sense, is embedded in the continuum. Now, it turns out that it doesn't matter. The fact that these departures are separated by random times rather than by fixed intervals, it turns out, is not important. It doesn't matter. Although you might not guess that at first. Okay, so that's the basic idea. And now, if we want to solve this kind of thing, what we have to do is determine the so-called, at least to begin with, I'm going to determine these so-called transition probabilities. Those are the conditional probabilities. So I've got to see whether or not, in fact, for a queuing system, it makes sense in that this depends only on that, so that it is, in fact, a Markov chain. Okay, you don't have to know anything about Markov chains, by the way. If you studied undergraduate probability or had a good course in probability, you should have come across the term Markov chains. And of course, there are whole courses on Markov chains. But from the point of view of our application, you don't really have to know anything about Markov chains from a technical point of view. We're going to use one theorem, and that theorem is intuitively obvious. Okay, so what are these transition probabilities? First of all, what's the probability that the kth plus first customer leaves behind j if the previous customer leaves behind 0? Okay, now if the previous customer leaves behind 0, what that means is this. There's the busy period, and it ended, and here's the customer we're talking about, and he leaves the system empty. So if customer number k leaves the system empty, then customer number k plus 1 must find the system empty. And if he finds the system empty, then when he leaves, the number that he leaves behind him are all those customers who arrived during his service time. So the probability that a departing customer leaves behind j if the previous customer left the system empty is equal to the probability that during this customer's service time, exactly j customers arrive. Well, we assume we have Poisson input. We assume that the service time distribution function is h. So dh of t is the probability that the customer's service time lasted exactly t. Lambda t to the j over j factorial e to the minus lambda t is the probability that during that interval of length t there were exactly j arrivals. And then I sum that as t runs from 0 to infinity. Okay, so that's this transition probability for the case in which I is equal to 0. That's equation 814. So this is for I equals 0 and j greater than or equal to 0, and it's 814. Okay, so what about the case in which I is not equal to 0? Okay, so now I'm going to calculate the probability that the kth plus first departure leaves behind j, given that the kth departure leaves behind I, where I is not 0. Okay, so going back to the diagram, it's something like this. Okay, so here is a departure, let's say. So if this is departure k plus 1, and this is departure k, and if the kth departure leaves behind I, the kth plus first will leave behind j if during this interval there are exactly j minus I plus 1 new arrivals. Okay, because this guy left behind I, this guy left behind j, so the difference between them is j minus I. But also we have to take into account the fact that this guy has left. So there's one more departure. So in other words, the only way that he can leave behind j if he left behind I, where I was not 0, is if during this interval of length t, that is during this service time, we have, according to a Poisson process, exactly j minus I plus 1 new arrivals. Okay, that's equation 815. Now, this of course assumes that I is greater than 0, because we already took care of the case in which I is equal to 0. And it also assumes that j minus I plus 1 is greater than or equal to 0. Right? Everybody in agreement so far? Okay, now, what about the case in which, well, we've got the case in which I equals 0 or doesn't equal 0, but when it doesn't equal 0, then we have the condition that j minus I plus 1 is greater than 0. So suppose that j minus I plus 1 is less than 0, then of course the probability is 0, because that represents something that's impossible. In other words, what this says is that the probability, for example, that this customer leaves behind 10, if the previous customer left behind 8, well, suppose the previous customer left behind 12. If the previous customer left behind 12, then the most that the next customer can leave behind is 11, because customers are departing one at a time here, and the inter-departure times are these service times. Okay, this is equation 816 in the text. So now if you look back over here, you can see that we have all of these so-called transition probabilities. Now, they may look complicated, but they're explicit, they're known, and furthermore, the important thing is to note that these things depend only on I and j, and they do not depend on k. In other words, it doesn't matter which pair of customers we're talking about, whether we're talking about the number of arrivals between customer 1 and customer 2, or customer 50 and customer 51. All that matters is that the times between them are separated by these service times, or by an inter-arrival time and a service time. Okay, so now I'm going to put that back in here. But in order to do that, to simplify things, let's see, I'll get rid of this. I'll scroll this way. What I'm going to do is I'm going to define Pj as follows. Little pj is going to be the probability that during a service time I have exactly j arrivals. And this is going to be defined for all j, 0, 1, 2, and so forth. So now, with this definition of little pj, I can see that this probability is little pj, and this probability is little pj minus I plus 1. And this probability, of course, is 0. Okay, so with that, okay, let me erase this piece here. So that means that these transition probabilities right here are given by little pj if I is equal to 0, that's this term, and little pj minus I plus 1 if I is greater than 0 and j is greater than or equal to I minus 1, and 0 if I is greater than 0 and j is less than I minus 1. Okay, so I could rewrite the theorem of total probability now, and I can replace this piece by these things. And the important thing is that as far as the transition probabilities are concerned, they're explicitly represented, even though it may look complicated at first glance, and they do not have any dependence on k, the number of the customer. Okay, so let me write that. In other words, this formula becomes the probability that nk plus 1 star equals j is equal to the sum over I of p nk star equals I times this stuff here. And that stuff there, in fact, I think I'll write it for the moment just like this. P ij does not depend on k. Actually, it's this, it's interesting that these PIJs, which is the usual notation that's used for a Markov chain, doesn't depend on I and j. Doesn't depend on I and j except through the difference I minus j. In other words, I only need one index to represent that stuff right there. But I don't care about that for the moment, because the argument I'm going to make is the following. What I really want to ask is, I don't care about the probability that the 58th customer, say, leaves behind a certain state. What I care about is the probability that a customer, an arbitrary, random, typical customer, leaves behind a certain state. In other words, I want to make the same our argument and observation that we made earlier, which is that what probably is of the most interest is the equilibrium distribution. After the system has been in operation for a long enough time so that the effects of the origin have worn off, then we're just talking about a customer without specifying which one. In other words, it's intuitively obvious that the following should be true. The limit as k goes to infinity of the probability that n sub k star equals j should exist. There should be a limiting distribution. Now, previously, we took the limit, we calculated the probabilities as a function of time, and we let t go to infinity. Okay, but now we've sort of gotten rid of time by embedding a Markov chain into the continuum, and now we're, in a sense, replacing time by customer, number of customers. And so we're saying that as k goes to infinity, the probability that the infinite customer finds a system in state j, well, there should be such a distribution. It should be independent of the initial conditions. So let's assume that it's true and call that pi j star. In other words, this is the equilibrium probability after the system has been in operation long enough so that the initial conditions have worn off, that a departing customer leaves j other customers behind him. Now, from a mathematical point of view, this is the mathematical content, because this theorem says that these equations have a unique solution in the limit as k goes to infinity. So this is actually a theorem from Markov chains, but it's totally obvious. It would only be interesting if it were not true. How could it be anything else? Now, of course, there's a condition under which this exists. In fact, what the theorem says is that this equilibrium distribution will exist, a unique distribution will exist if and only if a certain condition is met. And that condition, of course, is that rho, which by definition is lambda tau, must be less than 1. Okay, this, in fact, what we're going to do is we're going to assume that this exists, and then when we solve the equations, the answers will turn out to be in terms of rho, and you'll see that the answers won't make sense unless rho is less than 1. So that will show that if there is a solution, then rho must be less than 1, and you can also argue that if rho is less than 1, there must be a solution. But nobody would doubt that. The only question is, what is the solution? So the mathematical content of this is the existence and uniqueness of a solution. But from a physical point of view, that's obvious, and the question is, well, what is the solution? How do you get it, and what does it mean? Okay? Okay, so let me erase this. And now let me rewrite these equations So I'm going to take these equations and I'm going to plug in to these guys this. And then I'm going to take the limit as k goes to infinity. Now when I take the limit, since these guys don't have k in them, we already showed that, they're not affected by the limit. And when I take the limit, then all that happens is I replace this guy formally by pi j star, and I replace this guy formally by pi I star, and then I have a set of equations to solve. Okay, so those equations are given in the book by 820. This is 819, by the way. Okay, so right here is 819. Okay, so now I'm going to write 820. And actually, I could have written 820 down immediately, except I want to be very careful about this because this method of analysis, the embedded Markov chain, is the key to all the elementary stuff in queuing theory. Okay, I keep on saying elementary. Actually, the name of the course is Advanced Queuing Theory, but this stuff is what I would consider to be intermediate queuing theory. The elementary stuff was the first course. This is the intermediate stuff, and then the advanced stuff, well, we'll get to some of that by the end of the course. Okay, so here's what these equations become. The probability that that a departing customer in equilibrium leaves behind j is equal to. Okay, now we have this sum here. This sum runs from I equals 0 to infinity. When I equals 0, let's look at that term. That term, of course, is going to be the probability that the previous customer left behind 0. That's pi 0 star. Multiplied by the transition probability, which when I is equal to 0 is pj, given by this. So that's pj. Then we have the remainder of the terms, in which the sum runs from 1. Okay, so now looking at the terms as I runs from 1 on up, then I would say, now, I have the probability that the previous customer left behind I times the probability that during that customer's service time, the number of new arrivals was j minus I plus 1. Okay, that's this case where I is greater than 0. Okay, but this term appears like this only for j greater than or equal to I minus 1. But when I gets large enough so that that this doesn't apply, this applies, then these probabilities are replaced by 0. So in other words, this sum is going to run as I runs from 1 until I reaches j plus 1. And when I reaches j plus 1, that's the last term. And then after that, all of these transition probabilities are replaced by 0. Okay, so the theorem of total probability then immediately relates to this, reduces to this, if I'm willing to assume the existence and uniqueness of the equilibrium solution. Okay, so the probability that a departing customer leaves behind j is the probability that the previous customer left the system empty, and then during the, which means that the next arrival finds the system empty, and so the probability that when he departs, he will leave behind j is the probability that during his service time, exactly j new customers arrive. Or if the previous customer left behind I, where I was not 0, what that means is that as soon as he left, the next customer entered service, and then that next customer will leave behind j if during his service time, exactly j minus I plus 1 new customers arrive. Okay, that's it. Now we have to solve these equations. Okay, so now comes the other stuff that we prepared for in the course. I'm going to define g of z, the generating function, of these pi stars. So it's going to be pi star j, z to the j, summed as j runs from 0 to infinity. And the strategy is simple. What I'm going to do is I'll multiply through by z to the j, sum both sides, and then do some manipulation. The manipulation will then lead to an equation for g, and I'll solve for g. And then, of course, once I know g, I know all the information because, in principle, I could expand the g and I could get the pi stars. And in particular, I can differentiate so I can get the moments. And in fact, we'll see that we can, that based on this knowledge alone, we can actually get the whole distribution of waiting times. It's rather surprising. OK, so now this is equation 822. So now the question is just to do all this. OK, so if I multiply through, let's give myself a little bit of room here instead of having to rewrite everything. OK, so I'll multiply that by z to the j, z to the j, z to the j. Then I'll sum as j runs from 0 to infinity. J runs from 0 to infinity. J runs from 0 to infinity. OK, the left side, by definition, is g of z. So that's that. OK, now how about this term right here? Well, the pi 0 star comes outside the summation sign. And then what I'm left with is the summation. I think I'll write it. Pj z to the j as j runs from 0 to infinity. Now this is in fact a generating function. It's of the form pj z to the j, summed as j runs from 0 to infinity. What is it the generating function of? Well, it generates these little pj's, and those little pj's are these. And this probability, remember, is the probability that during a service time, there are exactly j arrivals according to a Poisson process. So it turns out, it looks like I'm not even going to have to actually evaluate this integral. All I need is its generating function. So for right now, just let me recognize that it is a generating function. So I'm going to call it h of z. So h of z generates the number of arrivals that occur during a service time. So this is really hopeful now. Things are really starting to look good. OK, now what about this piece? Well, that looks kind of messy. Just let me call that S. OK, so what I have to do is I have to do all this work here. All right, but in the book, of course, it just says something like, well, you interchange the order of summation, and then you apply some, I don't know, things you remember from calculus about how to do that, which I can never remember. So the way to do this when you're actually doing it as opposed to writing it in a book or paper is to simply write it out and then look what the terms are. So that's easy enough. So I'll do that over here. Of course, here I'm making use of all of these theorems from analysis that say that, see, I don't need this, that say that I can always interchange orders of integration, summation, all that kind of stuff. OK, so let's write out what S is. S is equal to, OK, first I'll write out the formula. It's a sum as j runs from 0 to infinity. Then I've got the sum as I runs from 1 to j plus 1 times pi I star p j minus I plus 1 z to the j power. OK, so the first thing I'll do is I'll take j equal to 0. And when j equals 0, then I have the sum from 1 to 1. So there's going to be one term in here, namely I equals 1. So when j equals 0, I'm going to get pi 1 star. That's this. J, now we said that j is equal to 0 and I is equal to 1. So when I is equal to 1, the minus I and the plus 1 cancels. The j is 0, so that would be p0. And since j is 0, that would be z to the 0. OK, so that's what that sum is when j is equal to 0. Now when j is equal to 1, then we're going to have the sum as I runs from 1 to 2. So the first term is going to have pi 1 star in it, and the second term is going to have pi 2 star in it, because I is running from 1 to 2. Okay, now, when j is equal to 1 and I is equal to 1, then this becomes little piece of 1, and this becomes z to the 1. And when I is equal to 2, then this becomes 1 less than that, so that would be p0, and that would be z to the 1. J is still 1. Okay? Okay, now what happens when j is equal to 2? Then I'm going to get pi 1 star. When j is equal to 2 is going to be the sum from 1 to 3. So there are going to be 3 terms here. The first one is going to be for I equals 1. So I'm going to get pi 1 star p2. This index will have increased by 1 because j is 1 larger. And z to the 2. The next term will be pi 2 star p1 z to the 2. And the next term will be pi 3 star. Is that right? P0 Z2. Let's see. P2 pi 1 star. P1 pi 2 star. Z, except that this should be, yeah, that's right. Everything looks right. Everybody agree?
Yes.
Okay, so now it's easy, right? I mean, I can see what the pattern is. So the next one's going to be pi 1 star p3 z cubed. The next one's going to be pi 2 star p2 z cubed. Then pi 3 star p1 z squared, no, z cubed, and then finally pi 4 star p0 z cubed. So you can see exactly what's happening. Okay, so I started off by summing this way, so now of course mathematics being what it is, being very contrary in nature, whatever it says to do, you do the opposite, you do the reverse. So now I'm going to sum down this way. Okay, so let's look at what I have here. If I sum down here, the pi 1 star factors out. And what I have left is p0 z to the 0, p1 z to the 1, p2 z to the 2. Well, that's exactly h of z. Okay, so that's great. Now we know we're on the right track. God wouldn't do this to us, to have it work out this way so far, and then all of a sudden in the last column not have it work. Okay, so what do we have here? Okay, this one is going to be pi 2 star. Now, this would be the same generating function, except that the power of z is off by 1. So if I divide it by z, no, I don't want to divide, yeah.
Factor out z.
If I multiply it by z,
Multiply z.
if I multiply it by z, then I'm left with p0 z to the 0, p1 z to the 1, and so forth.
hz.
And that's h of z. And then over here, you can see, now you see exactly what's happening. Okay, this one is going to give me pi 3 star times z squared h of z, and so on. Okay, so now let's see what S has become. When I calculate this sum, what I'm left with is pi 1 star h of z, pi 2 star zh of z, and so forth. So what do I have? The h of z factors out. Okay, so that takes care of that h of z, that h of z, and so forth. And then I'm left with pi 1 star plus, over here, z times pi 2 star, or pi 2 star z. And the next term is pi 3 star z squared, and so on. Okay, so this is beginning to look good. Let me give myself some more space here. Okay, now this would be a generating function, except that the z's are off from the subscript. The power is off from the subscript by 1. So if this were z squared and this were z cubed and so forth. So what I'll do is I'll divide by z and multiply by z. That's going to make a z here. And a z squared here, and a z cubed here, and so forth. Now, this thing here is, again, the generating function of h of z, except it's missing the 0th term. So therefore, this whole thing becomes h of z divided by z times 1 minus, or not 1. It becomes the generating function of the pi stars, which is g of z, minus pi 0 star. Because if I wrote this out, this g of z, it would have every term that's in here plus pi 0 star. So if I subtract the pi 0 star, then that thing there is the same as what's in parentheses there. So in other words, S is this. So that's just by ordinary arithmetic. And in the textbook, that's equation 828. Okay, so going back over to here, we see that g of z is equal to all of this plus s. And we've just worked out s to be that. So that's h of z over z times g of z minus pi 0 star. Right? Any questions, or did I make a mistake here? Okay, that equation in the textbook is equation 829. Okay, well now we're getting somewhere, because now we have everything in terms of g of z, which is what we want to find, and h of z, which presumably we know, because h of z is simply the generating function of the number of arrivals during a service time, and we know the service time distribution. That's our parameter in a sense. And this unknown constant pi 0 star, which of course we're going to calculate by normalization. Okay, so now if I solve 829, that gives me this result. G of z is equal to z minus 1 times h of z divided by z minus h of z times pi 0 star. That's equation 830. Okay, so we're getting there, but now we got to figure out what pi 0 star is. Okay, how do you figure out pi 0 star? Well, we know that g of 1 must equal 1. That's the normalization requirement. So if I plugged in z equals 1 here, then I should be able to evaluate pi 0 star. But when I plug in z equals 1, I see I have the problem that the numerator is 0 because of the z minus 1. The denominator is also 0 because since this h of z is a generating function, h of 1 is equal to 1. The denominator becomes 1 minus 1. Okay, so I have an indeterminacy. But that's no big deal. The way I evaluate that is I simply apply L'Hopital's rule. So L'Hopital's rule says that if you have an indeterminacy, what you do is you differentiate the numerator and denominator separately, and then plug in the value z equals 1. And if that works, that's the answer. And if it doesn't work, evaluate the derivative again separately and keep on doing this. Well, in this case, it turns out that this is an exercise in elementary calculus. One application of L'Hopital's rule will allow this to be done and allow me to solve for pi 0 star. But of course, pi 0 star is going to turn out to be exactly what we knew it was in the first place. Pi 0 star, of course, is going to turn out to be 1 minus rho. Now, we already got that, in fact, with our earlier derivation of the Pollaczek-Kitchen formula by using Little's theorem. So we know it's going to be true. Remember what we said was, well, pi 0 star must be the same as pi 0. And by pasta, that must be the same as pi. And pi 0. And pi 0 is 1 minus the probability that the server is busy. And the probability that the server is busy, while the server can have, in that sense, if I look at the server as being the system, it has only two possible states, either empty, idle, or busy. And so the probability that it's in state 1 is the same as the expected value. That's always true for a 0, 1 variable. We made this argument earlier. And that means that, pi 0 star is 1 minus the expected number of customers in the server. But then by Little's theorem, that's equal to the rate at which they enter the server times the average time they spend in the server. The rate at which they enter the server is the arrival rate lambda. The average time they spend in the server is the average surface time tau. And by definition, rho is equal to lambda times tau. OK, but we could do this by simply differentiating. Now, when you differentiated, the way where this rho would come about would be that when I differentiate the h and then plug in 1, that means that, well, what would I get for h prime of 1? If I have a generating function and I differentiate it, set the argument equal to 1, then that's equal to the expected value of the random variable that generates. And since this thing, h, generates the random variable that's the number of arrivals during a service time, then this part is the average number of arrivals during a service time. And the average number of arrivals during a service time is the arrival rate times the average service time. OK, so it's an exercise in L'Hopital's theorem to go from this statement to this statement. But it's no different than what we already know the answer to be. OK, so now I know pi 0 star, so the end result is that I know g of z. OK, so let me erase this and write that down for future use. OK, so g of z is equal to z minus 1 h of z divided by z minus h of z times 1 minus rho. Now, obviously, this doesn't make any sense unless rho lies between 0 and 1. So there's your condition right there. I mean, this is a generating function, so it certainly doesn't make any sense if rho is greater than 1 because that makes it negative. And physically, the problem doesn't make any sense if rho is less than 1 because rho is the product of the arrival rate and the average service time. So obviously, this is valid if rho is less than 1. If rho is not less than 1, then of course it doesn't apply. Now, this is one of the key results. This is actually also sometimes called the Pollaczek-Kitchen formula. There are various formulas relating to MG1 that are called Pollaczek-Kitchen formulas. OK, so this says in principle, you tell me the distribution function of service times, and from that I can compute the generating function of these probabilities. So in principle, if I know this, I know this, so I know this, so I know this, so I know everything. Now, another way of writing this is as follows. We had a theorem that says that if we have an interval which is random, and we have a number of Poisson arrivals during that interval, that there's a relationship between the length of the interval and the number of arrivals during the interval. Okay? We already know that. In fact, there it is. If the interval has distribution function h, the probability that during the interval there's exactly j arrivals is given by this. Now, if we take the generating function of this, which by definition is h of z, then what that means is I multiply this thing by z to the j and I sum it. And we already did that, and we saw that if we went through all the work, it turns out that the answer is the Laplace-Dirichlet transform of that evaluated at lambda minus lambda z. Let me do it. Okay, I'm going to calculate h of z. It's a summation of pj z to the j. I'm going to do it because we're going to use this result again. This turns out to be a very important result because this allows us to go back and forth between the generating functions of discrete variables and the Laplace-Dirichlet transforms of continuous variables. Okay, so that would be the sum of the integral 0 to infinity of lambda t to the j over j factorial e to the minus lambda t dh of t z to the j. All I did was plug in what pj is, multiply by z to the j, sum it. That makes it a generating function. Okay, then this is what we did before. We take the z to the j and we put it in here. And we bring the summation sign in here. And we sum that lambda t z to the j over j factorial. And so that becomes, when you sum that, that becomes e to the lambda t z. Okay, I take this z to the j and I combine it with a lambda t to the j. So I've got something, lambda t z to the j over j factorial, summed over all j, and that's the Maclaurin series expansion of e to the lambda tz. We already did this, so that's why I'm not doing total detail. So that sum becomes this. I still have my e to the minus lambda t. I still have my dh of t. And I still have my integral from 0 to infinity. And then I take this piece on the inside, and I say, but that's the same thing as e to the minus lambda minus lambda z t. Right? There's e to the minus lambda t, that's that guy. And then there's e to the plus lambda zt, that's that guy. Okay, so what I have here is I have the integral of e to the minus something t dh of t. Well, that's the definition of the Laplace-Dirichlet transform of the distribution function of the random variable whose distribution function is h. So what we've done, we've called that eta in the past. So if eta of s is the Laplace-Dirichlet transform of the distribution function of the surface times, then h of z is equal to eta evaluated at s equals lambda minus lambda z. Okay, so now this thing says, all right, you tell me the distribution function of surface times, h. So I can calculate the transform of that distribution. That's easy, ordinarily. At least it's certainly easy in principle. And that transform is directly related to this generating function of the number of arrivals that occur during a service time. So if I go back to this formula here, for g of z, I can go one more step. It's equivalent. It's just another way of writing it, but it's usually the way it's written, as z minus 1, and h of z is replaced by eta of lambda minus lambda z. divided by z minus eta of lambda minus lambda z times 1 minus rho. So in this form, it says, okay, this is really nice and neat now. It says, okay, you tell me the distribution function of service times. From that, I calculate the Laplace-Dirichlet transform of that distribution function. And knowing that, I know what g of z is. So this generating function is completely determined if you tell me what eta is. And if you tell me what h is, then you've told me what eta is. Now, this is the generating function of the number of customers left behind by an arbitrary departure. I can calculate the moments of that thing now by differentiating. For example, I can differentiate and set z equal to 1, and that's going to give me the expected value of the number of customers left behind by a departure. Well, of course, we know that that's the same thing by the arrival departure theorem as the expected value of the number found by an arrival. And by pasta, that's the same thing as the expected value of the number in the system as seen by an outside observer. But the expected value of the number in the system, that's related to the time spent in the system. And the time spent in the system is the sum of the time spent waiting in the queue plus the time spent in service. And the time spent in service on the average is tau, and so the end result is that using Little's theorem, I can calculate the expected value of the waiting time. Because I don't need Little's theorem, I'll get back to that in a moment. But if I did use Little's theorem, what I can get is this. I can say that the expected value of the waiting time is equal to the derivative of the generating function of the number evaluated at 1. Okay, this is now the expected number in system. So if I subtract off the expected number in service, then that would give me the answer. Now I'm going to go over this again later because I'm going to derive this directly. Okay, but I'm just saying now I'm going to break out and apply Little's theorem. Okay, that's where this row comes from. So just let me say quickly what I did here. The expected value of the waiting time is equal to what I would calculate if I differentiated this. Now, what I get here is the expected number in system, because it's the expected number left behind by a departure. Okay, that's the number left behind by a departure, the expected value of that distribution. But we know that departures see the same thing as arrivals because it's a one-step process. And we know that the arrivals see what the outside observer sees by pasta. So therefore, if I calculated the average of this thing right here by calculating this derivative, I would be calculating the average of that, which means I would be calculating the average number in system. But the average number in system, to get the waiting time, I would take average number in system and subtract from that average number in server. This is the carried load in the server. So this thing here is the average number in the queue. And then if I take the average number in the queue and divide by lambda, L equals lambda W, then I would have average time in queue. And average time in queue is average waiting time. And if I did that, I would get the Pollaczek-Khinchin formula. So it's an exercise, again using L'Hopital's theorem, although now it's more complicated. Because now, when I differentiate this, it turns out that the numerator and denominator will both be 0 when z is equal to 1. And when I differentiate again, it will still be true. So I have to differentiate twice. That is, I have to use L'Hopital's rule twice, differentiating numerator and denominator separately before I don't have indeterminacy. But again, it's just an operation in algebra, and an exercise in algebra. And when I do that, I will get exactly the formula we got before. Okay, but this is just a side issue for the moment. Next time what I'm going to do is I'm going to start with this, and I'm going to derive the total distribution of W, and then calculate the expected value from that. So it's amazing that by just embedding a chain at the service completion epochs, we'll be able to derive the whole distribution function of the waiting times. You would think there wouldn't be enough information in only knowing how many are left behind by a departure. But we'll see that next time. Okay, so are there any questions before we quit today? Okay, so now we're getting to the heart of queuing theory, and from the rest of the course now we'll be looking at particular queuing models using these kinds of arguments. Also, we'll look at some numbers and see what all this means. Okay, so see you next time.